Hi! In this episode, we'll talk about telescopes and the optical elements that go into them to create fabulous images of the universe which leave us spellbound. Do not worry if you have never studied optics before. We'll start from the basic principle and move up the ladder. So let's begin. This is a photo I took on the mountain summit of the island of La Palma in Spain many years ago. It is an unedited photograph taken with a basic mobile phone camera of the times, and yet I hope you can sense the sharpness and clarity in this image. That is because La Palma is the second best site for optical observations on Earth, succeeded only by the Hawaii island. Now you may wonder, why is it that the two best sites for astronomical observations are both tropical islands? Well, that is because both these sites are dry on the top of the mountains and offer clear skies for most of the year. Both these sites are also blessed with a tropical inversion cloud layer, which is around 600 meters thick in case of the Mauna Kea summit on the island of Hawaii. This inversion layer ends just below the summit thanks to its altitude and offers clear cloud-free view of the sky. In fact, if you notice carefully, you can see that even in this image from La Palma, the cloud cover is actually below the mountain summit, therefore providing opportunities to observe objects which may not be visible from anywhere else. But why do we need a telescope? A telescope does three main jobs for us. It collects light. That's why the bigger, the better. Secondly, it provides angular magnification, which means that the object appears bigger in size. And lastly, it resolves the object, that is, it helps us in seeing the finer details, for instance, here in the case of Jupiter. The field of view determines the angular size of the object that can be seen through a telescope. In simple terms, angular scale means the area of the sky, or specifically the object that can be seen through a telescope. The resolving power of a telescope is defined as the reciprocal of the smallest angle subtended at the objective lens or mirror of the telescope by two-point objects which can be separated from each other when viewed through the telescope. Think of it in the sense that there are two very close by stars, but if you are looking at them through a small telescope, you will see them as one big point of light, but a better telescope will show you that the two stars are actually separated by a physical distance. Mathematically speaking, resolving power is proportional to the ratio of wavelength to the diameter of the telescope. This implies that for a given wavelength, a bigger telescope will help us see finer details of an object. So big telescopes not just collects more light, it also helps us to see the detailed features in a distant object. Astronomers quantify the effect of Earth's atmosphere using a term called seeing. Astronomical seeing is defined as the average diameter of the image of a star which is assumed to be a point source as seen through a telescope. Seeing is measured in arc seconds. There are 60 arc seconds in an arc minute, and there are 60 arc minutes in a degree. For instance, as shown here, several images of the same crater of the moon taken at different times show slight differences which need to be corrected for in an image. Here is an example of some famous telescopes with their aperture size and the typical seeing obtained by them. Tell me in the comment section below, are you surprised that a big telescope in Hawaii actually performs better than the Hubble Space Telescope? This is the reason astronomers want bigger telescope at a good observing site. And telescopes such as the Very Large Telescope in Chile or the upcoming 30-meter telescope, also known as the TMT, will actually be able to perform better on the ground than the Hubble Space Telescope. Now let's talk about some of the common terms astronomers use to describe a telescope and define the properties of an image. Plate scale is equal to the focal length into tan theta, which can be approximated as f theta. In other words, dh by d theta gives you the focal length, where theta is the angle calculated in radians. 1 radian is equal to 206,265 arcsecond. So a telescope with larger focal length will form larger images at the focal plane. But the more area the light spreads over, the fainter will be the final image. This means that if you want to see faint objects such as galaxies, the focal length of the telescope should be small. But if you want to measure accurate positions of a bright source, for instance, a star, or if you are trying to find something that is far away, the focal length of the telescope should be large. There is another quantity called pixel scale, which is equal to pixel size into plate scale. Another interesting term in terms of telescopic optics is the focal ratio. This is the ratio of the focal length of primary to the aperture diameter of the primary, where primary is the mirror or lens which forms the image in a telescope. Here, for instance, are the specifications for the Hubble Space Telescope, which mention its focal ratio as f by 1.75. Basically, the f ratio tells you what fraction of the area of a lens is used for collecting light. If you see lenses used by professional photographers, for example, this is the number mentioned on the rim. A larger f ratio lens is used to observe nearby brighter objects such as Moon and large planets like Jupiter. Now that we understand some of these terms, let's quickly review some basics of optics as well. The Snell's law is one of the fundamental laws governing the properties of light. Basically, it tells you the relationship between the light in a medium incident on an interface of two different materials, say air and glass, and the light ray which emerges from the other end of the second medium. The index of refraction of a material is a dimensionless quantity calculated as the ratio of the velocity of light in vacuum to the velocity of light in a medium. Usually, the index of refraction increases with the density of the material. This is because a higher density implies more particles in a given volume of material. So, as the density of particles increases, more light gets obstructed and consequently the index of refraction increases. But do notice the subscript lambda in the denominator. That is the velocity of light in the medium and the left-hand side, which is the refractive index. The refractive index is a function of wavelength, which means light of different wavelength disperses differently when going from one medium to the other. In fact, the beautiful rainbow that we see is a result of this dispersion as light passes through the water droplets in the atmosphere. White light is split into 7 colors because they have different velocity in water. And the violet color disperses the most, which means changes its direction with respect to the incident light because it has the lowest wavelength. That is why the violet is always the innermost color in a rainbow. For a converging lens, the focal length f is positive and for a diverging lens, it is negative. The lens maker's formula, as given here, assumes that light is traveling from medium 1, which is air, to medium 2, which is glass. The end medium is refractive index and capital R represents the radius of curvature of the lens in each case. The refractive index of air is 1. This equation gives the relationship between the focal length of a lens and the refractive index of the medium. In case of mirrors, the relationship is simpler. That is, focal length is just half of the radius of curvature of the mirror. Another advantage of using a mirror instead of lens is that the focal length is independent of the wavelength. So one does not have to correct for the fact that different colors of white light will disperse differently. Therefore, it is not surprising that some of the largest telescopes in the world, such as the 10-meter Grand Telescopio Canarias on the island of La Palma, uses a mirror and not lenses. Another advantage of mirrors is that only one surface requires polishing and maintenance rather than two in case of lenses. For a given size of telescope aperture, the mirror will have a lower weight compared to a lens as well. Basically, there are two main types of telescopes depending upon whether the objective, that is the light collecting optical element, is a lens or mirror. If the objective is a lens, a telescope is known as a refracting telescope or just as a refractor, an example of which is shown here. The light from a point source enters through the objective lens as parallel rays because our object is very far away. The rays then converge, cross and diverge before going into the eyepiece and again emerging as parallel rays but in a smaller bundle which can be seen by the observer. The world's largest refractor is the 40-inch Yerkes telescope which began observations in 1897. As you can see, since the objective is a lens, the telescope tube is very long and therefore also requires a large dome, that is, a larger area for its operation. This is another shortcoming of a refractor in addition to the ones we discussed earlier. Next, we come to reflectors, which are telescopes with the objective as a mirror. Once again, assuming our source to be very distant, the parallel rays entering the telescope are reflected by the mirror, converge, cross and diverge again before going into the eyepiece and emerging as parallel rays which are observed in a smaller bundle. Some of the largest running telescopes in the world, such as the GTC mentioned earlier and the upcoming TMT, are reflecting telescopes. Here is a quick summary of the difference between reflectors and refractors. Depending upon the position of the eyepiece and whether or not a secondary mirror is used together with the primary reflecting mirror, reflectors can be further subdivided into different categories, 4 of which are demonstrated here. Let's look at them one by one. As the name suggests, in case of the prime focus reflector, the image forms at the focus some distance away from the primary mirror. Although now CCD cameras are placed at this focus to record the image taken by the telescope, that was not always the case. In the image on the left here, for instance, you can see Edwin Hubble sitting at the prime focus inside the telescope to see the image taken by the telescope. A Newtonian reflector uses a secondary mirror to reflect light through the side of a telescope. It is named after Isaac Newton, who invented and built the first reflecting telescope in 1668. Newton hypothesized that distortions called chromatic aberrations were caused in the images because lenses split white light into its spectrum of colors. So in order to avoid this problem, he started using a mirror as an objective. A Cassegrain uses a secondary mirror to reflect light back through a hole in the objective mirror. This design is attributed to Laurent Cassegrain, who first used it in 1672. The classical design used a parabolic primary mirror, but a modern version of a Cassegrain is the Ritchie-Cretin. All modern reflecting telescopes use hyperbolic primary and secondary mirrors in this kind of a design. Next in line are the Schmidt telescopes, which use spherical mirrors, but along with it also an aspherical correcting lens to correct for image distortions called spherical aberrations. The Schmidt-Cassegrain telescopes uses, in addition, also a secondary mirror to reflect light back through the objective mirror. Schmidt telescopes have been used by astronomers to study the large-scale structure of the universe by conducting surveys of galaxies, as we discussed in an earlier video. A classic example of a Schmidt telescope is the Palomar Observatory Sky Survey Telescope, which conducted one such galaxy survey in the early 20th century. Now that we have familiarized ourselves with the types of telescopes, let's take a moment to discuss the mounts, that is, the stand on which a telescope is placed. There are basically 2 types of mounts, equatorial and altitude azimuth or alt-az mounts. As shown here, in case of an equatorial mount, one axis is directed at the north or south celestial pole depending upon the observer's hemisphere. That is, this mount has a polar axis which is parallel to the Earth's axis and a declination axis which is perpendicular to the Earth's axis. Once pointed correctly, this telescope only needs to be rotated about the polar axis to track an object which appears to move in the sky with the same speed with which the Earth rotates, and is therefore popular amongst amateur astronomers and astrophotographers. But a disadvantage of this mount is that it requires a counterweight to balance the weight of the telescope and prevent it from falling when rotated on one side of the mount, as shown in this image of a 3.6 meter Canada France Hawaii telescope, which has an equatorial mount. The Alt-as mount, on the other hand, needs to be rotated vertically as well as horizontally to track an object across the sky. They are popular for large telescopes with motorized controls because they are cheaper and easier to build relative to equatorial mounts and also provide somewhat better control. But there is a problem. Since the orientation of celestial objects changes as the Earth rotates, this is a shortcoming for the Alt-as mount, which requires use of a field derotator. So at the end, let's quickly sum up the differences in the two types of mounts. I hope you would have learned something new about telescopes and optics today. Please do let us know what other topics you would like us to cover on this channel, and don't forget to like and share our videos with other astronomy enthusiasts. And if you haven't done so already, do subscribe to this channel. I'll see you next week. Until then, take care.